Section 4.7 is on inverse trig functions. There's a very specific domain and range for inverse trig functions, which I want you to see why that exists, but I don't need you to copy this because I won't ask you to do this again. Okay, so before I graph the inverse function, I'm going to sketch a graph of the actual function. So f of x equals cosine x. I'm going to make a little sketch right here. Okay, y equals cosine x looks something like this. It's periodic, it continues forever, left and right. And I'm going to do a sketch for sine x as well. Okay, that's my little sketch for g of x equals sine x. Now I'm going to go back to f of x equals cosine x. Now it's hard to imagine this, but if I imagine I am reflecting this function over the y equals x line, which is this line right here, somewhere around here, if I were to flip it across that line, it would make some kind of like squiggly shape going down, okay? If it makes that squiggly shape going down, it's not a function, it's gonna fail the vertical line test over and over and over again. Because of that, when you define the inverse cosine, you have to cut it off, otherwise it's gonna keep repeating in that weird wiggle motion, and it's gonna violate the function. Okay, so the way I'm going to do this is, let's see, I'm going to start at 0, 1, and I want to make sure I hit all the y values in the function exactly one time. I don't want to repeat them. Okay, so this starts at 1, it goes down to 0, it goes down to -1, and then if I were to keep going on the graph, and if you imagine this is like reflected, kind of imagine it turned 90 degrees. If I kept going, all of a sudden, it would violate the vertical line test right here. Okay, so I have to stop the function right here. So I'm going to graph the inverse cosine, which is also called the arc cosine, by looking at this graph. Since the x-axis only goes -1, 1, or the y-axis does, the inverse is going to go from -1 to 1 on the x-axis. And since the x-axis goes from 0 to, well, it's supposed to go from 0 to 2 pi, but I'm only going to go from 0 to pi. 0, maybe pi over 2, make this pi. I'm just switching the x and y axis. I'm going to regraph the inverse function. Okay, so this is 0, 1. Instead of 0, 1, I'm going to plot 1, 0. Okay, right here I have pi over 2, 0, which is going to be 0 pi over 2. And then down here it's pi -1, so I'm thinking -1 comma pi. This is where the graph of the inverse comes from. Okay, this is the graph of inverse cosine. Okay, now if I had not cut it off, it would have kept going and it would have wiggled backwards and it would have violated the vertical line test. That's why we cut it off. Okay, I'm going to do the same for sine. I want to cut it off so that it doesn't violate the vertical line test, which really means I need it to not violate the horizontal line test. Okay, so I'm going to start at 0. Okay, I'm starting at 0. I go up to 1. Y is 1. That's pretty good. Okay, I have to stop though, because if I go back down, look at it sideways, I'm all of a sudden going to fail the vertical line test. So I can't go any further to the right. So let me see if I can go further to the left. Okay, I can go back here. I can go back here. And then I'm going to stop here. Because if I look at this, if I had flipped it across the y equals x line, it would violate the vertical line test. It would no longer be a function. So I have to cut sine x off at -pi over 2 to pi over 2 in order to create the inverse sine function. Okay, I'm going to sketch a little graph of this. Since my y-axis goes from -1 to 1, my x-axis goes from -1 to 1. Since my x-axis goes from -pi over 2 to pi over 2, this is -pi over 2. Pi over 2. Okay, now I'm going to invert my points. So at -pi over 2, -1. So -1, -pi over 2. Let's see, at 0, 0. And at pi over 2, +1. So at 1, pi over 2. Okay, this is the graph of inverse sine. And it does get cut off because if it continued infinitely, it would keep wiggling back and forth and it would violate the vertical line test. Okay, so the domain for inverse cosine has to respect the domain of this graph because that's the only way to maintain it as a function. So in this case, the domain for inverse cosine is -1 to 1, including -1 and 1. The range for inverse cosine is from 0 to pi. Okay, now if I look at my inverse sine graph, which I drew carefully to respect the domain and range so I don't violate the vertical line test, the domain goes from -1 to 1, and the range goes from -π/2 to π/2. And we're going to use these domain and ranges in the definition of inverse cosine and sine on the next page when I actually have you start copying. But I want you to see this is where it comes from, even if you never ever see it again. Okay, I'm going to go ahead and sketch one period of tangent. Okay, now tangent only has a period of pi, so I can make this smaller. -π/2, alpha up. I'm going to go 1, -1. Okay, the tangent of 0 is 0. The tangent of π/2 is undefined. Tangent of -π/2 is undefined. And at π/4, the tangent is 1, so it goes up on the right, down on the left. Okay, so this is my graph of tangent going from -π/2 to π/2. It includes one period, which is fine. Now, if I imagine I am reflecting this across the y = x line, or really just kind of look at it sideways, if I only draw one period of it, it's actually okay for the vertical line test. It's going to graph okay, it's going to be fine. So let me sketch a graph of it over here. Since the x-axis was -π/2 to π/2, the y-axis is -π/2 to π/2. Since the y-axis is -1 to 1, the x-axis is -1 to 1. Okay, so since there was an asymptote at -π/2 and π/2, now there's a horizontal. Okay, let's see, 0, 0 stays the same. Let's see, π/4 was 1, so 1 is at π/4, which means it's going up on the right. It must be going down on the left. Okay, so this is the graph of inverse tangent. It passes the vertical line test, which is why I can extend it forever to the left and right, which means the domain is -∞ to infinity. Okay, now the range, it goes to -π/2, but there's an asymptote. So there's a parenthesis at -π/2. And then it goes to +π/2, and there's a parenthesis there because there's also an asymptote at y = π/2 on the inverse function. Okay, I'm going to flip to the next page, and we are going to start writing this down. But the domain and ranges for the next page come from these three graphs. Okay, so do write this down. This is saying for the inverse function of sine, which is also called arcsine, y = arcsine x, if and only if sine y = x, the domain is -1 is less than or equal to x is less than or equal to 1, and that matches the graph on the previous slide. The range is -π/2 is less than or equal to y is less than or equal to π/2, and that matches our middle graph. I am going to write on here, when you say arcsine, that's the exact same thing as saying sine to the -1 of x. Inverse sine and arcsine are the same. It's just a different way of expressing it. Okay, so for y = arc cosine x, which could also be written as cosine to the -1 x, the domain is -1 to 1, and it can equal both. But then we had to restrict the range from 0 to pi in order to maintain the functionality of inverse cosine. Okay, and y = arctangent x, the domain's -∞ to infinity because the graph of the inverse extended forever left and right. But the range was restricted between -π/2 and π/2, and that was based on the fact that there was a horizontal asymptote at both of those locations. Okay, now what does that actually look like when we're evaluating it? Okay, so for example, when we're going to evaluate and do an exact answer whenever possible. Okay, because the inverse functions are all functions, they give exactly one answer. Okay, so you should get only one answer. It's not like when we are solving and we pick a bunch of answers that fit the domain. The domain is restricted so that there is exactly one correct answer. Okay, so the first row is arcsine. Okay, for arcsine, I can input any value between -1 and 1, but my output should be between -π/2 and π/2, and it can equal -π/2 and π/2. So I'm going to draw a sketch to see what that looks like. Okay, -π/2 is down here. +π/2 is down here, which means any answer for arcsine must be on the right side of the circle. And because of the way it's written, if I go up, I'm going positive, and if I go down, I'm going to call it a negative answer. Okay, so now I'm thinking the arcsine of √3/2 is saying what is the angle when the sine value is root 3 over 2? Okay, this is one of the locations where the sine value is root 3 over 2. That's pi over 3. That's a valid answer because it's within that restriction. Okay, now if we were solving an equation, we might consider an answer that's over on this side, but because of that, that is out of the range of arcsine, I don't count it. Okay, now I'm going to do the inverse sine of negative 1/2, and this is the same as the arc sine of negative 1/2. So I'm looking at the unit circle to think about where the sine value is equal to negative 1/2. And since it's an inverse, I'm giving the angle as the answer, or the radians. Okay, so that would be down here. Okay, and I'm only picking answers that are within those two quadrants. Okay, because I'm going down, I have to give it a negative answer. So that's negative, and that's pi over 6. I can tell that looking at it. If you can't tell looking at it, you could call it 11 pi over 6 and then subtract 2 pi from it, and you'll still get negative pi over 6. Okay, now one more arc sine. This is the arc sine of 2. Okay, I don't see that on the unit circle, which doesn't mean it doesn't exist. It might mean we need a calculator to get an approximation, but I'm going to go back. The domain of arc sine is between negative 1 and 1, which means the input here has to be between negative 1 and 1 because 2 is too big. The arc sine of 2 does not exist. If you wanted to check in your calculator, you could. If you put inverse sine of 2, it's going to give you some kind of error. But again, arc sine 2 is not valid because it's higher than 1. The absolute value is higher than 1. Okay, the next row is all cosine, arc cosine. Okay, for arc cosine, again, I'm inputting a value between negative 1 and 1. My output is going to be between 0 and pi, and it could equal to 0 and it can equal to pi. So I'm going to sketch it so I can see what I'm talking about. This is 0, this is pi. So between 0 and pi means I'm only going to include answers for inverse cosine that are between 0 and pi in those two quadrants. The nice thing is it's always positive. Okay, let me see. So if I want to see where the cosine is negative root 2 over 2, but in these two quadrants, it's going to be at this point, and that's just 3 pi over 4. And that's a reasonable answer because it is between 0 and pi. Okay, now where's the inverse cosine of negative 1 is where the cosine value is negative 1, so that's over here. Because it is 0 is less than or equal to y is less than or equal to pi, it can equal to pi. So that's a valid answer. Okay, and then arc cosine of 1/2. Cosine's 1/2, that's right here. What is that? That's pi over 3. Okay, and I should be getting exactly one answer because these are inverse functions, and functions give exactly one y value for each x value input. Okay, next we're going to do a little arctangent. Okay, arctangent is very similar in its range to sine. Okay, so I'm negative pi over 2 to pi over 2 is over in those two quadrants. And the same rule applies that if I'm going up, it's going to be a positive answer. If I'm going down, it's going to be a negative answer. It cannot equal the pi over 2 and negative pi over 2, but that's because there's an asymptote there because it would be undefined at that location anyhow. Okay, let's see, arctangent root 3. I normally think about it like this. This is the y over the x. So I want the y value to have a square root 3, so that's up here. That's going to be at pi over 3. And that's okay, because that's between negative pi over 2 and pi over 2. Okay, the inverse tangent of negative 1. So that's at one of those root 2 over 2, root 2 over 2's, but I want it to be negative. So it's going to have to be down here at the pi over 4. Because I went down, I have to call it negative pi over 4 so that it will be in the correct domain. Okay, and then if the inverse tangent is positive 1, I'm thinking positive root 2 over 2, positive root 2 over 2, which is up here. Since I'm going up, this is going to be positive pi over 4. Okay, the last three are mixed up, but we are going to try them in our calculator actually, even though we don't use calculators often. Okay, so if I ask for the arc cosine of negative 0.235, this is a valid problem because the number in the parentheses is between negative 1 and 1. So it should be okay. So put inverse cosine of negative 0.235 in your calculator, and we are doing radians right now, so you might have to change to radian mode. Okay, so I got 1.808. Okay, and if you don't get that, just think, oh, you're probably not in radian mode, because for radians, arc cosine only goes from 0 to pi. So if you get a number higher than pi, you're not in radians. Okay, now arc tangent of 10, is that allowed? That's allowed because the input or the domain for arctangent is negative infinity to infinity. So I can put whatever I want in for inverse tangent. When you put in your calculator, remember you're doing the tangent to the -1 of 10, or second tangent. Make sure you are in radians, which means my answer should be between negative pi over 2 and pi over 2. So if I get a big answer, I'm probably in degrees. Okay, so I get about this. It's an approximation, and I would only do this if it's asking me to give an approximation. Let's see, arc sine of 10, is this allowed? Arc sine, for the domain or the input, the answer must be between -1 and 1. So this is not between -1 and 1. So in this case, it does not exist. Okay, and if you could put that in your calculator, it'll just give you an error message. Okay, now example 2 says, use an inverse function to write an expression for theta as a function of x. They're making this sound like it's a really fancy problem, but they just want you to use SOHCAHTOA. So they want you to write an expression for theta. So they want it to be theta equals, and then they want some kind of inverse function involved in it. Okay, first I'm just going to write this using SOHCAHTOA. Okay, this is theta, this is opposite, this is hypotenuse, so I'm going to use sine. So the sine of theta is x plus 5 over 7. Okay, now to cancel this sine, I would use inverse sine. So an expression for theta would be sine to the -1 of x plus 5 over 7. And that's all they're looking for. That's an expression for theta. And it is as a function of x. It's an inverse function of x. Okay, up next, it's the inverse properties. Okay, now because sine and arcsine are inverses of each other, they should be able to cancel each other out. So the sine of arcsine of x should equal to x, and the arcsine of the sine of y should equal to y. It seems like it should, because they're inverses of each other. This is IFF, means if and only if, but it's actually only true when you're respecting the domain and range of the inverse functions. Okay, so if the x is between -1 and 1, and it can equal them, and if the range is between negative pi over 2 and pi over 2, including the endpoints, then they will in fact cancel each other out. But if they are not in that domain or range, they will not cancel each other out. Okay, so the same is true of cosine and arc cosine. They should cancel each other out as long as you're within the correct domain and range of inverse cosine. And then for tangent, the same is true, except there's no restriction on the input of arctangent, but there is a restriction on the range. Okay, so for example 3, we're going to evaluate some compositions of functions and their inverses. Okay, and the point of knowing that they cancel each other out is to make your life easier. It's just that you have to be careful about it. Okay, so the first 4 are all going to be regarding arc cosine and cosine. So I'm going to sketch a little picture. Okay, remember the range of arc cosine is from 0 to pi. Okay, so if I'm checking the domain and range, I'm looking for that. Okay, so if I look at this, I have the cosine of pi over 4. I want the arc cosine of pi over 4. So do those cancel out? Okay, the only thing I have to ask myself, is pi over 4 within the correct domain? Yeah, it is. Because it's in the correct location, they're just going to cancel out, and I'll get pi over 4. Okay, for the next one, same. I'm just going to check and see if it's in the correct domain and range, and if so, I can cancel them. If not, I'll adjust. Okay, let me look at this. Okay, arc cosine. Okay, this is between -1 and 1. Okay, so that means the cosine and the arc cosine should cancel each other out. So this just goes down to -1/2. Okay, for the next two, they will not cancel each other out, so you can see what that would look like and what you would do to adjust this. Okay, so if I do the arc cosine of the cosine of 3 pi over 2, let's see. This is supposed to be between 0 and pi. It's not between 0 and pi. If I think about where that is on the circle, 3 pi over 2 is actually down here. Okay, but arc cosine must produce a result that is between 0 and pi. So I'm going to look at this, and I want to find a location on the unit circle that is between 0 and pi, but has the same cosine value as this value, which is the cosine here is 0. So if I want to fix the domain, if I go right up here, this also has a cosine equal to 0, cosine value of 0. So this cancels to pi over 2. Okay, so it's not exactly that it cancels. It relocates into the correct range and then gives you an equivalent answer within the correct range. Okay, last arc cosine. Arc cosine of the cosine of 7 pi over 6. Okay, again, I'm just checking. Okay, 7 pi over 6, that's not between 0 and pi. If you're visual, look at the circle and then go 7, oh no, 7 pi over 6 is in the wrong place. Okay, so where is 7 pi over 6 is about down here. Okay, I want to find a location on the unit circle with the same cosine value, but that is in the correct range for our cosine. So x coordinate, let me take it up to here. This has the same x coordinate, so it has the same cosine value, but this one happens to be 5 pi over 6. Okay, now I'm respecting the range of arc cosine. Okay, E and F and G have to do with arc sine. So I'm going to think about the domain and range of arc sine. It's negative pi over 2 to pi over 2, and the domain's negative 1 to 1. Okay, so let me see. If I do the arc sine of the sine of negative pi over 3, okay, is negative pi over 3 in the correct location? Yeah, that's between negative pi over 2 and pi over 2. So these will cancel, and it will go straight to negative pi over 3. Okay, now if I do the arc sine of the sine of 5 pi over 4, is 5 pi over 4 between negative pi over 2 and pi over 2? No, it's not. 1, 2, 3. It's over here. Okay, so I want to find another answer on the unit circle that is in the correct range of arc sine, but has the equivalent sine value. Sine is the y value. So this y value should match over to this y value. Okay, so this was 5 pi over 4, but it has the same y value as this thing. Since I'm going down, I have to call it negative. So this is negative pi over 4. This way I'm respecting the range of arc sine. Okay, now the next one's a crazy decimal, so I have to think about it. Now G is the sine of the arc sine of 0.8. So the input of sine, arc sine, I'm sorry, should be between negative 1 and 1. That's between negative 1 and 1, so it should cancel. Okay, now let me look. H is arctangent. Arctangent actually has a similar range as sine, so I'm going to use the same picture. Okay, now our tangent of the arctangent of 100, that's not on the unit circle. The input for arctangent has to be between negative infinity to infinity, so that's acceptable. They should cancel each other out. That's fine. Okay, and then the last one, the arctangent of the tangent of 5 pi over 3. Okay, now 5 pi over 3 is 2, 3, 4, 5. That's down here. Okay, so the location is in the correct quadrant, but the naming of it is not okay, because if I'm in this quadrant, I have to call it a negative name. So instead of calling it 5 pi over 3, I need to rename it negative pi over 3. Okay, or if you don't like that visually, you could do 5 pi over 3 and subtract 2 pi, so you can rename it with a negative coterminal angle. Okay, the last example is on composition of functions. Okay, this is like what happens when you're mixing up your functions. So this is the sine of the arc cosine of 2/3. So they don't match. So we actually have to do a little bit of work here. Okay, some people like to draw a picture for this. There's multiple ways to do this. Okay, so I'm going to sketch a little picture, I think. Although you might want to do it a different way once you see what we're doing. Okay, let's call this U. Okay, it says the sine of the arc cosine of 2/3. So I'm trying to find the sine of which angle produces a cosine of 2/3. Okay, so let me draw a little picture. This is going to be x over r, which would be 2 over 3. You don't have to draw a picture. I could also do x squared plus y squared equals r squared here. I want to find the sine of this angle. So that I could rewrite this as sine of u. I don't have to though. Okay, the sine of u would be the opposite over the hypotenuse. I don't know the opposite side, so I need to solve for it real quickly. So 2 squared plus y squared equals 3 squared. Doesn't have to be y. I'm just trying to match the people who will use the XYR method. So y equals root 5. Which means the sine of u, or the sine of this angle, is root 5 over 3. Okay, and you might draw a picture. You might use XYR. I don't know which method you would use. It's up to you. Okay, for B, we're going to do the cosine of the arctangent of -3/4. Okay, because there's a negative, it makes it a little bit trickier. Because with all positives, I know I'm in quadrant 1 and I don't even think about it. Okay, so let's see what we have. I know that tangent is y over x. I don't know if the y is negative or the x is negative. I could draw a picture. I could do multiple ways to do this, but I do need to consider the fact that this is arctangent. Because this is arctangent, I have to either be in quadrant 1 or quadrant 4. Those are my only two options. Okay, now if one of them is negative, I must be in quadrant 4. So if I'm in quadrant 4, the x is positive and the y is negative. So one way would be to use this ordered pair and then find the r from that. I'll do it this way. This time I won't draw a triangle. I'll use the ordered pair. So r equals the square root of 16 plus 9. Okay, so I want to find the cosine of the angle that produced a tangent of -3/4. So now that I'm going to find cosine is going to be the x over the r. So the x I found was 4, the y was 5. So I would get 4/5. And you could do it a different way, but we should get the same result. Last one's C. It has an x in it, so it's going to be an expression. So it's the tangent of the arcsine of 2x. Okay, the one nice thing is everything is positive, so I'm thinking quadrant 1. So I don't really have to worry about the signs so much. So I can make a triangle, I could do an ordered pair, I could do this various ways. I'm going to draw a triangle, but I'll show you, if I did an ordered pair, I'll also show you what ordered pair I might use. Okay, let's see, this is over 1, so opposite over hypotenuse. Okay, and if I was doing it with the XYR, I would make my y 2x and I would make my r 1. And that would be how I would get the answer. Since I'm making a little triangle, I'm going to use the Pythagorean theorem. What am I going to label? I'm going to label this a, just because I don't want to confuse it with the x. Okay, so Pythagorean theorem, a squared plus 2x squared equals 1 squared. Make sure you square the 2 and the x. 4x squared equals a squared equals 1 minus 4x squared. So a is going to equal to the square root of 1 minus 4x squared, and because I'm in quadrant 1, a is positive, whereas if I was in a different quadrant, that might not be true. Okay, so what am I actually trying to find? I'm trying to find tangent. Because I did a triangle, it's over a. Yours might be y over x, depending on how you solved it. So O over a. What's a? This ugly thing. Okay, because this is so ugly, I'm okay with you leaving it like this, unrationalized. But if you want to rationalize it, it would end up looking like this. they're both fine. Because nothing cancels, it doesn't look any better. It doesn't matter to me which way you do it.